Hi everyone. So for today we're doing strengths of acids and bases. Our syllabus outcome is to write ionic equations to represent the dissociation of acids and bases in water, conjugate acid-base pairs in solution, and to construct models and/or animations to communicate the differences between strong, weak, concentrated, and dilute acids and bases. So, revision from last lesson. Make sure you've done the questions before going through these answers. So pH is a logarithmic measure of hydrogen ion concentration. Each tenfold increase in hydrogen ion concentration decreases pH by 1. So pH equals negative log 10 hydrogen ion concentration. Hydrogen ion concentration is 10 to the negative pH. So remember that first one is on your formula sheet, the second one's not. We also have the POH equivalent. So POH is negative log 10 OH minus. And concentration of OH minus is 10 to the negative POH. And lastly, POH plus pH is 14. Now, strengths of acids and bases. So here, have a look at this picture. We can see that we've put some metal into two different acids. One of them is bubbling a lot, one of them is bubbling not so much. And that's because not all acids and bases have equal reactivity. Okay, in the picture, there's two acids of the same concentration, but one's reacting more vigorously than the other. And why is that? Well, it's the strength of the acid and the base. Okay, so it's due to the strength of the acid. In all of our pH calculations we've done so far, we've assumed that all of the acid in solution is dissociated. But it's not the case for most acids and bases. Okay. Only some of the acid will dissociate or donate a proton. Now, strong acids. Strong acids are acids that will completely dissociate in solution, and they will readily donate their protons to water molecules. The most common strong acids that we deal with are hydrochloric, sulfuric, and nitric acid. Most of the rest are actually weak acids. So here's our strong acid. So we can see HCl completely dissociates the H plus and Cl minus. Nitric acid completely dissociates the H plus and nitrate. And sulfuric acid completely dissociates the two H pluses and our that's sulfurous acid. And that gives us SO3 2 minus, so sulfite. Weak acids. Now, on the other hand, weak acids are ones that don't completely dissociate. And they're less able to donate protons. So acetic acid is an excellent example of this. So acetic acid, actually, I think it's about 1 in 1,000 molecules will dissociate and the rest won't. Other examples include hydrofluoric acid, so HF, nitrous acid, and formic acid. So if you ever see any of those, they're weak acids. So acetic acid actually exists in an equilibrium. So some of the acid dissociates, but the rest will reassociate in the reverse reaction. So we've got that dynamic equilibrium going. We have acetic acid on the left, which is in equilibrium with our hydrogen ions and acetate ions on the right. It's dynamic equilibrium. We have that forming, we have it reassociating, we have it dissociating. Okay. Now, at any one point in time, there's usually only about 0.4% of the acetic acid present in its dissociated form, so as that acetate and H+. The change depends on a wide variety of factors, like how concentrated the solution is, the temperature, and all of that. But that's the average. So having a look at a bit of an example of this. So on the left, we have a strong acid. So we can see that in the pipette, all of the acid is associated, so they're bound together. But the second it hits water, they all dissociate. So the H plus and the negative ions have all come apart. Now, weak acid, on the other hand, we can see that only part of it has dissociated. So we can see that there's plenty of the acid and proton combined together in the water, and a few of them are dissociated. Okay. Strong bases. So they're, again, they're bases that completely dissociate in solution. They readily accept proton from the more acidic substance such as water. And the most common strong bases that we deal with are always readily soluble hydroxides, such as sodium, potassium, or calcium hydroxide. Our weak bases, they're similar to weak acids. They don't dissociate completely or accept protons less readily. Examples include ammonia, sodium carbonate, and sodium bicarbonate. Now, what I want you guys to do, this diagram's in your booklet. So I want you to label the beakers below as either strong or weak acid, as well as concentrated or dilute. So remember, a strong acid is one that completely dissociates. Okay, there will be positives and there will be negative ions. Weak acid only partially dissociates, so you have some positives, some negatives, some with no charge. Remember, concentrated means the concentration's high, dilute means the concentration's low. So have a go at that, and we'll go through the answers in just a sec. So here we are. First one is strong and concentrated. So you can see everything's ionized, they're all pluses, they're all minuses, and there's a lot of them there. Second one is strong but dilute. Third one is weak but concentrated. And the fourth one is weak and dilute. Now, conjugate acids and bases. So this is a bit of terminology that you guys will have to get used to, especially when we start doing Ka and Kb and buffers. So having a look at this reaction. So here we have acetic acid reacting with water. So it donates its proton to water. We get hydronium, so H3O+, plus acetate. Now, in this example, we can see that the acetic acid on the left has acted as a Bronsted-Lowry acid and donated its proton to water. The water acts as a Bronsted-Lowry base, accepting that proton. But what happens in the reverse reaction? Well, let's have a look. So it does go backwards. So when we go backwards, the H3O+ acts as an acid and donates its H+ back to the acetate. And the acetate acts as a base and accepts it. Okay. So when it's reversed, the H3O+, or a hydronium ion, acts as an acid and donates a proton. In other words, it's now what we call a conjugate acid. The acetate ion in the reverse reaction acts as a base and is called the conjugate base. Okay, so remember, in the forward reaction, if it acts as an acid, it will react as a base in the reverse reaction. So that means on the left it will be an acid, on the right it will be its conjugate base. And vice versa as well. So in this one we have water acting as a base in the forward reaction, which means it acts as a conjugate acid in the reverse reaction. So let's go do some examples. Okay, we'll label this one a bit better first. So we can see that acetic acid acts as an acid in the forward reaction. Water acts as a base. In the reverse reaction, our H3O+ acts as an acid, so it's our conjugate acid. And our acetate ion acts as a base, so it's the conjugate base. So here's some further examples where I want you to label the acid, the base, the conjugate acid, and the conjugate base. Okay, so have a go with that. See if you can find out which way, who's donating, who's accepting protons, label them appropriately. We'll go through the answers in just a moment. Okay, HNO3 plus H2O gives us H3O plus NO3 minus. So here we have HNO3 becoming NO3 minus, so it has donated a proton. So it's acted as an acid in the forward reaction. Water acts as a base and receives that proton. In the reverse reaction, our H3O+ can act as a conjugate acid by donating that extra proton that it's got. And our nitrate can act as a conjugate base, accepting the proton in the reverse reaction. Now, going down to the next one, ammonia plus water is in equilibrium with ammonium and hydroxide. So let's have a look at the NH3. The NH3 acts as a base, becoming NH4+, so it has accepted a proton, so it's a base. Water, on the other hand, has donated a proton, so it's an acid in the forward reaction. Ammonia, after it has acted as a base, becomes ammonium, And in the reverse reaction, ammonium can donate its extra proton and go back to being ammonia. So it is a conjugate acid. And in the reverse reaction, we have OH minus that can act as a base, accepting a proton, becoming water again. So it's a conjugate base. Now, we just have to do a little bit on strengths of conjugate acids and bases. The stronger the acid, the weaker the conjugate base. Okay. Yeah, basically the strength of our conjugate acids and bases is opposite that of the original acids and bases. So strong acids produce weak conjugate bases. Weak acids produce strong conjugate bases. So let's have a look at this diagram on the right here. We can see at the top that we've got HCl. We know that's a pretty strong acid, okay? It becomes Cl minus. But Cl minus is not a very good base. In fact, if we just put sodium chloride in water, it stays neutral. That's how bad of a base it is. Okay, if we move down a bit though, we have HF and F minus. So HF is starting to get on the weak side of being an acid, okay? It will donate its proton to become F minus, but F minus will just gladly accept a proton and go back to being HF. Okay, so they're pretty equal. On the other hand, down here, H2O is not a good acid. I mean, pure H2O has a pH of 7. It's not great at all. But after it donates that proton and becomes OH minus, that becomes a really strong base. Okay, so it changes that pH down to like, 14 sort of thing. And so it really wants to take somebody else's proton and become water again. So a summary for today. So strong acids and bases are ones that dissociate completely. Weak acids and bases only partially dissociate. Acids in the forward reaction become conjugate bases in the reverse reaction. Bases in the forward reaction become conjugate acids in the reverse reaction. And strong acids produce weak conjugate bases, and weak acids produce strong conjugate bases. Okay, so that's all for today. Make sure you have a go at those questions, and I'll see you next time.